Welcome back again. Today we are going to wrap up our exploration of optics by talking about the eye and about vision, and also a little bit about polarization. Polarization gets included in this because certain creatures on the earth and under the sea actually do see polarized light, can perceive it. And in fact, human beings can as well. We'll talk about that very briefly. So the general idea of today's lecture is vision. It's one of the more interesting topics I think we cover. I know it's a topic that many of you are interested in, the eye and vision correction and things like that. So I'm looking forward to the next 50 minutes or so. So let's get started. We'll begin with this question. So this is a question about vision correction. You can see the clever title of the slide, Seeing Things, because glasses is how people see things. Nothing? All right. Next step is to add a laugh track. So let's think about this question. Which best describes how glasses or contact lenses, they work in the same way, help a person see better? So look at the different options. Pause the lecture. Go to the quiz and give your answer. Which of these do you think best describes how glasses or contact lenses can help a person see better? All right. Well, hopefully you've come back. Turns out the answer is B, that in fact glasses really don't change how your eye works. They don't change your eye's ability to focus on things. They change the appearance of the world to fit what your eye can do. Correcting vision doesn't actually correct vision. It corrects the world. It corrects an image of the world, provides you one that maps onto what your eye can do. So if you have trouble seeing distant objects, then vision correction like glasses or contact lenses will give you images of those distant objects that are close enough so that you can actually focus them on your retina. I think that's actually fascinating. It's something I've never thought about. And I do wear glasses. You probably have never seen me in glasses. I don't need them for much. I just need them to see distant objects. But when I am wearing them, it's really interesting to think that I am kind of seeing this illusion of a world that maps onto how I can see. Well, I think what people would normally think. All right, well, let's think about the eye a little bit. It's an amazing thing. It lets us do quite a bit. Focus in on this thing called the crystalline lens, which is a lens that can change shape. It can become thicker or thinner as needed in such a way that objects get focused on your retina. So the purpose of the crystalline lens, the cornea, is to focus rays from objects outside of your eye onto your retina, to create real images on your retina. So here's a question. Suppose you are watching a distant object approach, something that's far away and getting closer. As you do, what happens to the shape of your crystalline lens? What does it need to do in order to allow you to focus on an object that's getting closer and closer and closer? So think about that a little bit. This ties together a number of things that we've been talking about over the last few weeks. Pause the lecture, give it some thought, go to the quiz, and say what you think. All right. So let's see. Now, as this object gets closer and closer, the rays from this object are going to enter your eye at a steeper and steeper angle. So the distances here are drawn just for convenience. So here I have my object that's far away. Let's say that's far away. The closer it gets, the steeper those rays from the object get, the more my eye has to work to bend them so that they can be focused onto the retina here. So it's very difficult actually to focus on nearby objects. That's why people have near points, that their eyes just can't do it after a certain point. It takes more effort to focus on nearby objects. Your eye has to bend the light more to get it to converge on your retina. Well, we already have seen that thicker lenses bend the light more. They're stronger. They have more power. And so as an object approaches you, your crystalline lens is going to thicken up. It's going to get thicker. It's going to get greater power. It's going to bend light more. And then it's going to reach a limit, and that is your near point. Okay, another question for you. Images projected onto your retina by your cornea and crystalline lens are inverted. That is, you see the world upside down. Is that true, or is that just a myth? So, pause this, give it a little bit of thinking. You actually have the tools to know whether this is true or not. And open the quiz, say what you think, come back here and we'll talk about it. All right. So here's the thing. When your eye creates images of the world onto your retina, they are real images. They're the sort of images that you could project on a screen, the screen being your retina. Well, what do we know about real images? All real images are inverted. So actually, the world is inverted on your retina. It is true that you see the world upside down. Now, your brain compensates. But those images are projected on your retina upside down, which is really kind of interesting. And we can tell that because we know they're real images, and real images are always inverted. All right, let's move on. So I want to do a couple of quick exercises to begin to set up how you might understand why certain lenses would be prescribed for certain kinds of visual corrections. So let's say this. Let's say we have a converging lens. So you can just tell by the shape, this is a converging lens. I have an object right here. It's giving off rays. Now it's giving off rays, of course, in all directions. I'm just drawing some of them here, the blue ones. They enter this lens and are bent as shown. Which of these, A, B, C, D, will be the image of this object through this lens? So look at the picture. The picture's also in the quiz. Pause the lecture, go to that quiz, and figure out which of these images, A, B, C, D, would be the image of this object. Okay, so how do we do this? Well, let's say we are over here looking at all of this. What would we see? Well, we would see rays that appear to come from back here. That is A. So if we backtrack these rays, as our eye will do, as our visual system will do, we would see an image at A. We wouldn't see the object directly. We would see it appear as if it were at A. So if you put an object near a converging lens, now this object would have to be inside the focal length. You can get it to appear further away. So converging lenses can create virtual images. That's the important part, we'll get to that, that look further away than the objects. If you put that object within the focal length of the converging lens, it will create a virtual image that looks further away than the object. And which will be upright. That's an important part too. Virtual images are upright. You don't want your glasses to give you inverted images. So you need to create virtual images. All right, let's try another one. Another picture, another object, another lens, this time a diverging lens. Which of these points, A, B, C, D, will appear to be the image of this object? Or maybe there is no image form. That's a possibility. So, pause the lecture, look at the picture, see what you think. All right. So we can pretty much do the same thing we just did, that is kind of backtrack these rays. If we were out here looking, here we are, we would see rays that appear to come from point C. So it would look to us as if point C were the location of this thing. Now, what can we conclude from that? Diverging lenses create virtual images that look closer than objects. That's actually always true of diverging lenses. The object can be at any point within the focal length or outside it. The image created will always appear to be closer than the object. So that should give us some hints about which lenses we would prescribe for different kinds of conditions, for different sorts of visual correction. So let's think about that. Let's imagine we have a person who's farsighted. And farsighted means you can see far. So this person can see distant objects. They have trouble seeing close up. Essentially, and here's a picture of an object near to the person's eye, they can't quite focus the rays from that object onto the back of their retina here. Maybe the eyeball is a little bit short, or the lens is a little bit weak. For some reason, they cannot focus those rays on the back of their retina. And so they end up, for when objects are nearby, they would see something fuzzy. Okay, what kind of lens do you think this person needs to help them? So, look at the picture, think about the things we just did. Go to the quiz, pause the lecture, obviously, go to the quiz, and give an answer. What kind of lens do you think this person needs? Okay, so what kind of lens would we give this person? Well, turns out you would give them a converging lens. A couple of different ways at this. We already decided that if you put an object inside the focal length of a converging lens, you can create an image that's further away. Well, this person can see further. So if we create an image of this object further away where they actually can focus on it, that would allow them to see it. Another way to think about it, let's say we give this person a pair of glasses, this converging lens. What's going to happen? Now let me get a different color to make this more obvious. What am I going to pick? I'll try blue. So the problem is that this person isn't able to focus these rays onto the retina. What this converging lens will do is sort of pre-focus, pre-bend the rays. So the rays will come in from this object. They'll be bent going through the lens, not too much, but enough that they are coming into the cornea and the crystalline lens at a slightly shallower angle, and therefore they can be bent to hit the retina. So, in a sense, like I said, a converging lens would pre-bend the rays and allow the person's cornea and crystalline lens to actually focus them on the retina. The other way to think about this is that this converging lens would create an image that's further away where the person can focus. So that would be the function of a converging lens for somebody who's farsighted. All right, let's try this. What kind of lens would you prescribe for a person who was nearsighted? Now, somebody who can see nearby objects but has trouble seeing objects that are distant. Pause the lecture, think about it, go to the quiz, and give an answer. All right. So nearsighted person may have an eye that's slightly elongated. They may have a lens, crystal lens that can't relax enough. Essentially, they have trouble because they focus rays before the retina. If an object is far away, their eye's kind of working too hard. it's trying to focus these rays here rather than back on the retina here where it could create an image. So again, you're going to get this fuzzy image. These rays will cross one another and create this fuzz, this blur that the person will see. So what do we want to do in this case? Well, you might have just guessed that it's going to be a diverging lens. And a couple of ways around this. We could say that a diverging lens will create an image of the object that's closer, that appears closer where the person can actually focus on. So if I put a diverging lens here, say in a pair of glasses, it will, I'm going to draw a slightly different set of rays here. So I have these rays coming out. They will be bent outward by the converging lens. I'm going to create an image that looks as if it's here. So this is an image that's close enough for the person to focus on. Now, what's going to happen is by bending these rays out, by having these rays diverge, you're actually making it a little harder for the person to see. You're bringing objects closer, their eye has to work harder, but that's what their eye wants to do. So by bending these rays out, you will allow the person's eye to actually focus them on the back of the retina. Remember, lenses can bend rays so much. This one's bending them too much. You give it a little bit of a steeper ray to bend, and it will, as long as you make the steepness appropriate, it will bend it so that it focuses on the retina there. You kind of unbend the rays a little bit so the eye has to work harder. All right, so that can give us some clues about what kind of lens we would need for which kind of situation. So let's take a practical kind of example here. Let me get some appropriate color here. So let's imagine we have a person who's farsighted. That should give us a hint already about what kind of lens we need. They have a near point of 100 centimeters, so they can't see anything closer, than 100 centimeters. They would like to be able to see objects 25 centimeters away. You need to prescribe a certain lens. What power lens would you prescribe? Now, we're going to assume that these are not contact lenses, these are glasses, so they do sit a little bit away from the person's eye. Very often in these questions there will not be this stipulation, but just to make it a little bit more challenging, that's what we're going to do here. Now, I would highly encourage you, when you have a question like this, draw pictures, because it's especially if there's some separation between the eye and the glasses, it's going to come in really handy to have that picture. So here I'm going to draw the person's eye. There we go. Here is the lens that we need. Now, I'm going to draw it as a converging lens. Kind of know, for a farsighted person, we're going to use a converging lens. But it's possible maybe I didn't know what kind of lens we needed. I could just leave that as an unknown. We will solve at the end and see that we did actually need a converging lens. So, here I have the object that they want to see. That object is a certain distance away from them, 25 centimeters. That's the distance between their eye and the object they would like to see. Meanwhile, there's a distance of 1.5 centimeters between the eye and the lens. Now, in order to see this object, you have to turn it into an image that the person can actually focus on. And here's a crucial detail. It has to be a virtual image. It can't be a real image. It can't be on the same side of the lens as the person's eye. That would probably mean an image somewhere behind their head. You still want the world to appear as if it's on the other side of the glasses. You want the image to appear on the same side as the object, just at a different distance. So we need a virtual image. And we need a virtual image at a distance this person can focus on. So here's my virtual image. And I stress that virtual because when we start to plug things into equations, that virtual means that I'm going to have a negative sign. So here I have my virtual image. Now this virtual image needs to be 100 centimeters away from the person's eye because that's what they can focus on. Again, we're matching the world to the person's eye. Okay. So if we want to find the power of the lens, we need to find the focal length. Remember that power is 1 over the focal length measured in meters. So really this is a question about finding the focal length of this lens. Here's where the complexity kind of comes in. This 25 and this 100, they are not image and object distances because they are distances from the person's eye, not the lens. So what we have to do is translate into image and object distances. This is our object distance. This is our image distance. Well, you can kind of see already what we're going to end up doing is subtracting 1.5 from 25 and 100. That's going to give us our object and our image distance, and that's what's going to allow us to solve for the focal length. So the object distance is going to be 25 centimeters, but I'm going to have to subtract this 1.5 centimeters between the eye and the lens. That's going to get me 23.5 centimeters. All right, good. And it's a positive number. All of our image distances are going to be, object distances are going to be positive numbers. Our image distance. Again, it's a virtual image, so I'm going to plug in the negative sign right away. I cannot forget that. I don't want to drop it. Then I take 100 centimeters minus the 1.5 between the person's lens and their eye. I'm going to get minus 98.5 centimeters. All right, so now I have my object distance and my image distance. Again, I need this to be virtual. I can put these into the lens equation. 1 over f is equal to 1 over di plus 1 over do. I know everything there except f, which is the thing I want to find. So let me plug in. Now, I need to keep this negative with my image distance. That's crucial. And then 23.5 centimeters. If I add all of this up, I get 0.0324 inverse centimeters. I flip everything over. I'm going to flip both sides of the equals. So I get f is equal to, and notice this is a positive number plus 30.9 centimeters. That plus tells me that it is a converging lens. So if I was in any doubt, I now know it is a converging lens. So from this I can get the power. The power is 1 over the focal length in meters. That's 0.309 meters. That gets me 3.24, and we measure power in diopters. All right, so that's the answer. These kind of questions are pretty standard. Sometimes you will have this distance between the eye and the lens, sometimes you won't. A contact lens sits right on the eye, and so there won't be any extra distance. Sometimes it's going to be a converging lens, sometimes a diverging. All right, so that's vision. Slight change of topic, something connected to vision, and that's polarization. I like this a lot. I mean, there are lots of animals on the earth that can actually detect polarization. This is a mantis shrimp. I didn't know about these until a student, somebody in a previous version of this course, sent me an article about mantis shrimp. There's a video that you can watch, that I think you did watch in the pre-lecture material. One of the organisms on the earth that can actually detect polarized light. There are others. There's certain excuse me, kinds of fish that can detect polarized light. Octopi can do it. Bees can do it. We'll actually talk about bees in a second. So certain animals can detect the polarization of light, just like it's a sense like detecting color, for instance. What does polarization kind of add? Well, it adds a certain kind of contrast. So it could be helpful for maybe finding prey or avoiding predators. You might be able to detect an organism even through camouflage. So it has some advantages. It has special advantages in the ocean where things are a little bit murky and dark anyway. So any extra added benefit that you can get visually, any added contrast you can get is an advantage. It turns out human beings can also detect polarization. It's not easy. It's a very subtle effect. It's called Heidinger's brush, something that sometimes you can see looking at computer screens, sometimes you can see it looking up into the sky. I have never personally seen it. I've tried. I've never quite gotten there. There is this Wikipedia entry. I would suggest maybe if you're interested, you go check that out. And if you do successfully see this, let me know, because I'd really be interested. Human beings do apparently have the capacity to detect polarized light. It's just not something that we really notice. So how does polarization come about? Well, you've seen this in the pre-lecture. There are a couple of ways in which you can polarize light. Light enters the atmosphere from the sun. That light is unpolarized. It'll hit air molecules. If you notice, here's our unpolarized light. And these are electric fields. These are electric field vectors. All these electric field vectors are kind of in this plane. So when it hits the air molecules, it'll cause the air molecules to jiggle back and forth if they have any charge, or up and down. So if you are looking up at the sky like this, you're seeing molecules just move back and forth. That creates light. That motion of charged particles will create light that is polarized in this way. And so when you look straight up, you're going to actually see polarized light. And this is, as I've read, how bees find their way. It's one way in which bees navigate. Bees can detect polarized light, and knowing that polarized light comes from straight above allows them to fly in ways that help them get places. They can kind of navigate by knowing which direction is straight up. You can also get polarized light through reflection, and this is where a special angle called Brewster's angle comes in. Theta sub b, this is Brewster's angle, and if you hit some interface, if you reflect light off an interface at Brewster's angle, and now the important thing to note is this is the angle from the normal, not from the surface, but from the normal, you can create polarized light reflected off the surface, and then partially polarized light that gets refracted down through. This is another reason why organisms in the ocean can often detect polarized light more frequently than organisms on land. It's because you actually do get a fair amount of polarized light in the ocean through this process. So let's, excuse me, let's take a concrete example. Let's imagine that we are watching the light reflected off Lake Mendota. At what time of day is that light likely to be fully polarized? So we're going to assume the lake is nice and flat, and we're also going to specify the index of refraction of water is 1.3. Now, in order for this problem to work, it actually can't be summer. I'm sorry to say. I know we're heading into that season. It's got to be winter. You'll see why in a second. But let's say it is winter, and the sunlight is reflecting off the ice. Ice actually has a similar index of refraction to water, so we'll continue to say it's 1.3. What time of day are you most likely to see fully polarized light reflected off that ice? All right, well, pause the lecture, go to the quiz, think about this a little bit, think about what we learned about Brewster's angle, and see if you can come up with an answer. Okay. So here's the thing. So we've got light that's hitting the surface of this frozen lake. What we want is that light to hit at such an angle that the reflected light is polarized, that is at Brewster's angle. So here we have the surface of the lake. Here we have the incoming light. It's going to be reflected off. We want this to be polarized. Now, have to remember that we're going to measure Brewster's angle not from the surface of the lake, but from the normal. So this is Brewster's angle. That's the angle that we're going to find. And we have an equation to find Brewster's angle. We take the inverse tangent of two indices of refraction, n2 over n1. Now, we've got to keep straight which is which. That n2 is the material the light is reflecting off. And this is just something to memorize. That n2 there is the material the light is reflecting off of. In this case, that would be ice. So we're going to use our index of refraction 1.3. n1 is where the light is coming from. In this case, the light is coming just from the air, and so we would use the index of refraction of air, which is just 1. So when we plug numbers into this, I take the inverse tangent of 1.3 divided by 1. Indices of refraction have no units. I'm going to get an angle out of that that's 52.4 degrees. If you want degrees, make sure your calculator is set to degrees. If it's set to radians, you're going to get another number. All right, so I know that Brewster's angle in this particular circumstance is 52.4 degrees. That isn't really telling me about the angle of the sun in the sky. When people measure the angle of the sun in the sky, they're talking about the angle from the surface. So if this angle from the normal is 52.4 degrees, that makes this angle from the surface 37.6 degrees. So I want the sun to be 37.6 degrees high. That's about where it is in midday in winter, which is why we needed this problem to take place in the cold months of the year. Very early in the morning and just before sunset, the sun would be too low. If it's right along the horizon, you will not get light coming in at Brewster's angle, and you will not get full polarization. All right, so let's think about another question about polarizers, materials that will allow us to let certain kinds of polarized light pass and block other kinds of polarized light. Before we do this, why don't you pause the lecture? There's a demo on polarizers that you can go take a look at. You'll see polarizers in different orientations to one another. You'll see how they affect the light that gets through. And then come back here and we will talk about this particular question. All right, so after looking at that demo, you now have a little bit of experience with polarizers. They're interesting. Here's a question. Many sunglasses have polarized lenses because reflected light is often polarized. And these polarized sunglasses help to reduce glare. All right, so suppose we were looking at this frozen lake with our sunglasses. We want to choose sunglasses that are going to eliminate the glare off the lake. Now, remember that the polarization of this light is going to be parallel to the surface of the interface where the light's reflected. If you go back a few slides, you'll see that. The oscillation of the electric field is going to be back and forth horizontally as the light is reflected. We're looking at the light coming at us and seeing the electric field go back and forth like this. So we want to choose glasses that are going to prevent that light from reaching our eyes. Which pair of glasses would we want to pick? Which orientation of polarizer would we want to pick? So pause the lecture, go to the quiz, make your selection, and come back. Okay, so which kind of polarizer would we want to pick? Well, the thing about the transmission axis of the polarizer, it's telling you what kind of light can get through. So for instance, we know we don't want A. If we had sunglasses with polarizers oriented like the picture in A, all of this light would get through and we'd see tremendous glare. So A is a no-go. What about B and D? Well, so we know that the electric field that's coming at us is horizontal, like this. So this is the, let's say it's the maximum electric field in this EM wave. the axes of polarization in these two polarizers are not in the same direction as this electric field, so it's not going to let everything through. But it will let some through. So we have to kind of go back to vectors. If I take this electric field and I take two components, one like this and one like this. So I'm going to call this component EB and this component ED for reasons that should become obvious soon. So these two are components of the electric field vector of the light. As this electric field passes through B, B will allow the component of the field along the transmission axis through. So it will allow this component through, which means some light will get through. Likewise, D is going to allow this E sub D, it will allow this through, this component of the electric field. The only polarizer that's going to stop everything completely is C, because the polarization axis is at right angles to the E field of the light. So really nothing can get through. There is no component of this horizontal electric field that can get through a vertical transmission axis. Okay. So, this is a single polarizer. What if we stack up multiple polarizers? This is a pretty common question on a quiz or an exam. And it can get complicated pretty fast. So let's give you a complicated situation to practice with. Let's say we have unpolarized light incident on these four polarizers that are oriented as shown. And we know the angles of the transmission axes from the horizontal. So the first one, the transmission axis is just horizontal. The next one, it's tilted 30 degrees from the horizontal. The next one, 60. The next one, 90 degrees from the horizontal. Okay? So let's ask this question. What is I4 in terms of I3? Now, just to preface this, here's the way in which we can label things to make it understandable. The incoming light we'll call having an intensity of I naught, the initial intensity of this light coming in. After it passes through the first polarizer, it has intensity I1. After it passes through the second polarizer, it has intensity I2, third polarizer I3, and finally, after it passes all four polarizers, we'll say it has I4. So what we're really interested in this question is the relationship between these two. So here is polarizer 1, 2, 3, and 4. How can we relate I4 to I3? So, think about this. Look at this picture. Think about what you learned in the pre-lecture about polarizers and polarization. Pause the lecture, go to the quiz, and answer this question. Okay, so here we are. I want to know, what is I4 in terms of I3? Well, if I start with I3, after I pass through the fourth polarizer, I'm going to get some change. What is that change? It has everything to do with the relative angle between these two polarizers. So let me actually try a different color here. So light that passes through the third polarizer will be polarized along its transmission axis. That transmission axis is oriented like this. It's 30 degrees off the transmission axis of the fourth polarizer. Notice I'm not really paying too much attention to these actual angles. What I'm paying attention to is the difference between them. So the difference between them is 30 degrees. So when I write my intensity, I'm going to use that difference. So the intensity that gets through I4 is my initial intensity, the intensity that is incident on the fourth polarizer, that is I3, times the cosine squared of the angle between the polarization of light, that is the transmission angle of the third polarizer, and the transmission angle of the fourth polarizer. And I've already decided that's 30 degrees. Which of those answers is it? That's C. So if I know I3, I could tell you I4. Okay. And all of this is all about vectors. If you go back to the pre-lecture and watch the slide on polarization, this all goes back to vectors and vector components. All right, so let's try this. Now that we know this one little piece, maybe we can do more. What is the final intensity of the light if the initial intensity is I naught? So we're going to say I naught is the initial intensity incident on these 4 polarizers. What is the final intensity of light? It's going to take a little bit of time. Pause the lecture. If you need to go get some water, something to eat, absolutely do that. Spend a little time with this. See if you can figure this out. Answer the question on the quiz and come back and we will work through it together. All right, hopefully you've made a good attempt at this. These polarizer questions can be a little tedious, but they do follow a pretty standard route. Okay, so in doing these, you kind of have to work backwards. I'm going to go back to the previous slide. So I know this relationship. If I know I3, I know I4. But I could do the same thing between I2 and I3. I could write a relationship between those two and plug it in here. So then I'd know I4 in terms of I2. Well, I can also find a relationship between I1 and I2. So I can find a relationship between I4 and I1, and so on and so forth. You step backwards, bit by bit, until you get to the original intensity, and that's what I'm going to do. So I'm going to start with what I know, which is I4 is I3 times cosine squared of 30 degrees. Well, what is I3? It's I2, and if I look at the relationship between I2 and I3, I've actually got the same thing I saw between I3 and I4. So the light that gets out of the second polarizer is polarized along its transmission axis. That transmission axis is 30 degrees away from the transmission axis of 3. One's 30 degrees from the horizontal, one's 60 degrees from the horizontal. Again, I'm not interested in the actual angles of their axes. I'm interested in the difference between 2 subsequent polarizers. All right? So if I plug that in, then I3 is I2 times the cosine squared of 30 degrees. And I multiply that by the cosine squared of 30 degrees. Now, what's I2 in terms of I1? Take my next step back. Well, if we go back here, same thing, actually. If I look at the transmission axis of I1, it's horizontal. The light coming out of I1 is all polarized horizontally. What's the difference between that and the transmission axis of 2? Well, 30 degrees. One more time. So let's go and plug that in. So I2 is I1 times the cosine squared of 30 degrees times the cosine squared of 30 degrees. My 3's are getting a little hard to read. There's a lot of them. So what's I1 compared to I naught? Well, here's where things get a little bit, not tricky, but it depends on what kind of light is incident. And it's important to note here, this is unpolarized light. If I sent unpolarized light through any polarizer, what's going to happen is I will lose half my intensity. There's 2 options for light incident on a sequence of polarizers. Either the light starts out polarized, and then to get from I naught to the intensity through the first polarizer, I have to take the difference between the initial polarization angle of the light and the angle of the transmission axis of that first polarizer. Or the light's unpolarized, and then I just know that the intensity through the first polarizer is just going to cut out half the light. So I've got that, and then I've got 3 cosine squared thetas. In this case, theta being 30 degrees. So and if I do all of that out, what am I going to get? I'm going to get 0.21 plus this I naught C. Okay, so like I said, a little bit tedious, but it's just following step by step by step. Now, here's another question. Suppose we do this. What will happen to the final intensity of the light if we remove the middle two polarizers? So look back at the sequence of polarizers. Pretend we take the middle two out, so we just have 1 and 4 left. What's going to happen to the final intensity of the light after it passes through polarizer 4? Think about that. There's a pre-lecture or bridge set question that might be relevant here. You might want to go look at that too. Go to the quiz, pause the lecture obviously, go to the quiz, answer it, and come back. Okay, so I'm going to go back to the picture of the polarizers. What am I going to see? I'm going to remove these two. Well, then what happens? I now have a polarizer that has a transmission axis that's horizontal. Another polarizer 4, this is essentially vertical. Or sorry, I've reversed those. This one, oh, you know what? These are this is totally messed up. These should all be vertical. Gosh. So it didn't change anything about what we just did because, again, I don't really care about the actual angles of these polarizers. I only care about the differences between individual polarizers. So this, let's just say I did this on purpose to teach you a lesson. The actual angles don't really matter. The differences between the angles do. 90 degrees from vertical is horizontal. So in the picture, at least, I'm matching that now. So I've got one polarizer with a vertical axis of transmission, the other polarizer with a horizontal axis of transmission. There's no light that's going to get through that. They are, what gets through the first polarizer is going to be vertical. There's no component that's horizontal. It's going to be 0. So actually, by adding polarizers, you can allow light to pass through, even though you've added more polarizers. It's a little bit counterintuitive, but it's possible. Okay, that's the end of this lecture, and that's the end of our journey through optics. We're about to embark on the last unit of the course, which is all modern physics. We will start with a little bit of reference to light, and then we'll move into some other topics. So, next time I see you, it will be in some review capacity. Everybody stay safe, stay healthy, and I will see you again soon.